components. Number 2, initial terminal. That's fill-in stuff, right? Number 8, multiplication, addition. Number 14, there's the initial. There's the terminal. There's the component form. And there's the magnitude. But wait, should you guys have just written a V? No, you better make sure you have an arrow on top. Make sure your notation is proper. There better be an arrow on top of him too. Woo! Should be showing your vector arrows. Number 22, initial point, boom. Terminal point, boom. Components and magnitude. We know how to simplify radicals, right, cool kids? Right. Thinking algebra teacher. Keep going. Number 42. Those were the original vectors components, right? To find the unit vector, you had to find the magnitude, which I think ended up being 13, true? And divide each component by 13. So, final unit vector in components, 5/13 and -12/13, and yes, that should end up with a magnitude of 1, because it's a unit guy. There he is, right here. Final answer, where my cursor is. 5/13, -12/13. Number 54. Was it easy cheesy just subtracting?
Yeah.
Oh my goodness. Components 3/8, linear combination 3i, 8j, but wait, look at your I, look at your j, what better be on top? Oh, yep. Number 72. You had to plug into the formula, or sketch it. Maybe you could have cheated on this one. Plug into the formula with magnitude cosine angle and magnitude sine angle for the horizontal and for the vertical. Solve, 0, 4√3 in components for this vector. If you guys had graphed it, you probably figured out the point 0, 4√3 as well. Number 96, I think that's our final even. Yep. Number 96, force, 600. Direction, 14 degrees. You were able to use our little formula, our little triangle, and hopefully you ended up with 2,480.1 pounds of force due to weight. What was that? Probably like the gravity. Was that the gravity? I think so. Because remember we talked about how W was like G and they were combined and they worked together. All right, a couple more seconds. Do you guys have any questions on the odds? The vector section? No question on the odds? This is weird. Okay, what's that?
I did something legal.
Yeah.
Did I go right?
Yeah, want me to check the work?
49.
Okay, 49. Oh, Cosette, that was yours, right? 49?
Yeah.
Perfect. We have a couple questions on that. Anything else besides number 49? Going once. Going twice. Trying to get your book. Hold on, I think it's in this one. Is this it? I think so. Nothing else besides 49, huh?
Yeah, 49.
Okay. Let's go check it out. We're in chapter 6. We're in section 3. Kiddos, while I get this open, can we go ahead and check our calendar real fast? Hold on, 6/3. Not much has changed, but some of you haven't paid attention. But we looked at it last week, so hopefully you're paying more attention. Our goal today is to, and that's not you. I'm in pre-cal. Sorry, hold on. You're like, what? We're in honors. Okay. Okay, our goal today is to finish 6/4, start 6/5. Our goal tomorrow, come on, is to finish 6/5 in order to, on Wednesday, be able to review in order on Thursday to have our test so that you don't have to try to do it on a minimum day. And you can have no homework over the 2.5-day weekend if we do it right. Hey. So we're going to work a little.
What are we doing?
Minimum day would be that.
Minimum day, we are at noon, I think. At lunchtime?
The classes are what if
12:30?
you take like half the test Thursday and then half the test Friday?
And we just took one period.
What we're going to do with the other half of the day Thursday. We'll see how bad it is. Oh, we'll just do something. Okay.
A
Nicole!
lot of review for chapter 6.
I can't hear Nicole! Shh, shh, shh. We're starting chapter 7. Despicable Me, we'll see. But we have to fit the test in on Thursday or else we can't have fun on Friday. All right, here we go. This is done. Let's get out of him. Oh, what's wrong with you guys? Okay, 49?
3, yes.
Oh no!
Like you say, Miss D.
We're working hard, but for a good purpose.
Ready, Miss D?
Okay. Number 49, what do you do?
Miss D, I drew it, and then I used similarity of triangles.
Okay, that probably would work, but technically there was a faster way to do it. Do you guys remember how the faster way to do it is?
Oh, you just double it, because you know it's 5.
We want this given magnitude, right, which is 10. And we have this given vector. Well, question, guys, we have to figure out who his magnitude is to be able to compare, don't we? And that's kind of Luca's idea with similar triangles. So what is the magnitude of u? 5. Yeah, we can do Pythagorean theorem, right? So that's a 3, 4, 5 triangle, so we can say his magnitude is 5. If we need him to be a length of 10, or a magnitude of 10, all we got to do is double him. So if we need to double that guy, who else are we going to double? That guy and that guy, right? So what are the components of the new vector, which has a magnitude of 10 and is in the same direction as negative 3, 4? Negative 6, 8. So it was a little weird in the question that it was asking. However, not impossible. Oh, you can put them on my desk. Thank you, Eddie. All right, cool kids. So no other questions on the vector section. Yeah.
But I used the similarity, and I thought it was more like a, you work this time, but I don't know if it would always work. Shouldn't, if I'm doing this similarity, shouldn't I do 10 squared over 5 squared? Shouldn't I use it squared?
Not squared, because that's for Pythagorean. Similarity says that sides are proportional, so just this side, not the square of the side.
And I can still use the hypotenuse.
Does that make sense?
Yeah.
Okay. All right, cool kids, let's go ahead and get out of this. I guess we're good. I don't really know. I'm a little surprised we didn't have more questions. Okay. Here we go. Notes open. I'm going to go and back to my little perch, and we'll keep going. Section 6.4. We started this on Friday. What was the title of 6.4? Vectors and dot products. Vectors and dot products. Is that the same as scalar multiplication? Is it like multiplying a vector by a number?
Yeah. Not really.
It is multiplication, but not that kind. Is it like vector addition? Adding two vectors together. It's an operation, but is it as easy? Let me go back. Let's find honors because I was on regular. There we are. And let's get you guys up on the screen. Okay. Where did we stop then? Not there. First page there. Not there. First page.
And I just started.
You got it? Vectors and dot products. More involved operation. Scalar multiplication and vector addition and subtraction are operations, but they're easy ones. They're easy ones. This one is still easy, to be honest, but it's very unique because it's not what we would expect. Some of you would instead expect us to do something like first, outer, inner, last. Wait, what? But that's not it at all. Don't do that. We are multiplying two vectors together, vector u and vector v. And how do we do it? What is this symbolizing, cool kids? Yeah, the horizontal components. So you multiply the horizontal components. Plus, and then what do you multiply? The vertical components. You multiply the horizontal plus you multiply the vertical. And then you literally take the two numbers, you add them together, and you get a constant answer. We would call it also a scalar answer. So what we get is not a vector. Now we're just going to see a few things as to how this can be used, how it can be applied, but once again, this is not a physics class, this is a free physics class. looking at the math involved in some of the physics operations. So we're just trying to get the idea. Down below, you guys do have the properties, and since the dot product is different, since it behaves differently, I would write these down. We didn't write the ones down that were easier and made sense. And even though some of these might be easy and make sense, there's a few, especially like number 4. It's a bit different that we might not have expected. Vector v times vector v is the magnitude of v squared. And here's another one that technically you guys should know, but I'm pretty sure you guys still would get pretty confused. When you have a constant outside u dot v, like with algebra, the constant only goes to one piece. It's not addition, it's not subtraction, so therefore it does not distribute to both. It's only allowed to go to one. From here on out, whenever you or I say this right here, you guys see what I'm talking about? This right here? This one? Okay. Whenever we say that, we're not going to say u times v. Did you hear what I said a second ago? U dot v. Not u times v, u dot v. Because they're vectors, multiplication behaves differently, we'll say dot instead of times. It's going to be a little weird, take some getting used to, but we'll be fine. We'll be fine, we'll be fine. The highlighted ones are the most important. You could write the others, but I think the others make a little bit more sense. So we'll just put those in parentheses. How about? Not that direct, but the ones that are unique are definitely properties 4 and 5. How are we doing? We close?
Good.
Oh. If you guys looked on the homework sheet, 6-4 is kind of short, by the way. BT dubs. So it's not totally crazy that it's doing, okay? You guys can do it. Yeah. Yeah. Before I change the page, really quickly, check your work. Did you do what Karina was just asking? Do all of these have little every single one? Oh, I caught some of you. I caught some of you. Remember, bold letters can appear in the book or in my notes, but they better not appear in yours. Right. All right. So, what do we do? With a moo! Where do the arrows need to go? Everywhere. 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 You guys tracking? Yeah. Alright, so I'm just fixing the notation just to remind you guys of what's going on with vectors. However, how would you do the dot product for number 11?
Just plug it in, right?
Careful, you don't need the I, you just need the component or the coefficients. So 4 times. Careful. Not 2. Maybe 2. Does that make sense? Take the coefficients of the horizontal components, so 4 and 1. Plus, take the coefficients of the vertical components, negative, it's minus, so plus and negative. Negative 2, negative 1. Dot product ends up equaling elemental mathers. Where are you?
4 plus 2.
Oh man, it is Monday. You guys are killing me. It's a number.
Whoa.
It's
Oh,
a number.
I thought you used component form.
Nope. Because it's not a vector anymore.
Oh, okay.
Dot product ends up being a scalar, a very important scalar that's used in all sorts of different stuff in physics, but he's not a vector. He's not a vector. So wait a minute, how do we do the one down below? Use your properties carefully. Okay, what do we got? Okay, -4. Right? Because the horizontal of V times the horizontal of U. Careful. Plus, dot product is always adding. Just to keep it the same direction, can I do 2 times 3? Is that okay? Minus. So there's the dot product of the first. Now I need the dot product of the second, right? So how do we do W dot V? Horizontal times horizontal plus vertical times vertical. Pause, hold on. Everybody tracking with where those numbers are coming from. Not check out V, we were taking him piece by piece. Then we were taking U piece by piece. So that's why we got the horizontal of V, -4 times the horizontal of U, 3. Then we did the vertical of V, 2 times the vertical of U. There we go. Now we're not done. Obviously we have some PEMDAS to do, but you guys see where the numbers are coming from now? Horizontal times horizontal plus vertical times vertical. That's the dot product in words. So PEMDAS, we gotta work inside those grouping symbols. Mental mathers, what do you got for the first one?
-6.
Close. -6. -12 plus 6. -6 minus, alright, what's the next one? -12 minus 2 is -14. Minus a negative, boom, boom, and mental mathers. Got it. Dot products result in scalars, constants. So I'm not even going to graphically show this to you guys. It's a little too complicated. We're not going that far. So for vector multiplication, a vector times a vector dot vector.
Ooh. Honestly, this is a really easy section.
Yeah, it's not bad. Now we have to see it applied, and that might get a little funny. But remember, I said if you're going to see a word problem on the vector test, it's going to come from section 6.3. It's going to be like the ones that we did, yeah? Something on an incline, something with tables, something with a plane flying and wind. One of those 3. But I didn't say section 6.4, which is kind of nice because, we haven't gotten to word problems yet, but they might get a little messy. Here's one application of the dot product. It helps us quickly solve for an angle between 2 vectors without having to use the law of cosine. It helps us quickly find the angle between 2 vectors without needing to use the law of cosine. So really it's an alternative. It's not necessarily easy. But it is an alternative, and it does show you one application of the dot product. Everyone better be showing your notation. And actually give you points for the correct notation on the test. I just got to do it cheaper, so maybe not that good. Wait, when are you guys going to get your test back? Test corrections are due when? But then we're like, we're working hard for a test on Thursday. How does Monday sound? Oh, yeah.
We can't correct them, the formula part of it.
You guys said you do a random 100. But a test correction is a test correction, so Luca, I figured I'd cut the work in half.
Okay.
So you only have to correct the problem and you still get the same 100 as if I made you correct more. You can see the formula portion if you want to come in and look if you're wondering why you lost points.
Mhm.
So as long as the two vectors are in standard position and we have their components, we have their information, we just need to set cosine of theta equal to the dot product of u and v all over magnitude of u and magnitude of v. So let's review, guys. Let me try to get that formula so you can see it. As we get that example down below, we got to get all of our pieces, right? So we need to find, first of all, u dot v. Then we need to find the magnitude of u. Then we need to find the magnitude of v. And then we plug and chug it into our calculator using cosine inverse. Is that okay? To solve for theta, don't we have to get rid of cosine first?
Yeah.
Okay. How do we do u dot v? So horizontal times horizontal is, which is 12, right? Plus vertical times vertical, 0. So therefore dot product will be 12. Is that okay?
Yep.
How do we find magnitude again, given components? Okay, think of it as a graph. Think of it as a graph. You go over 1, 2, 3, go up 2. I know this one. I know this one. I want to know this one. Remember?
Yeah.
It's as easy as, Sean, say it louder. Pythagorean theorem. So 2 squared, 4 plus 3 squared, 9 is 13 square rooted. Is that okay? Can we shortcut the process with the next one?
You see, how is it legal to go from head to head? Okay.
Ah, it's subtraction, not addition. It's subtraction, not addition. So when they are working independently of each other and when we connect, we never show this graphically. When we connect them working against each other, it's the subtraction instead. Here's the reason why.
I'm just gonna go like.
Yeah, subtraction, wouldn't that make it u and negative?
Yeah.
And a negative u would be going this way.
Mhm.
Does that make sense?
Yeah.
So it's negative u plus v or v minus u.
Makes sense.
I'll keep that one there. Coming down, magnitude of v, we have to do 4 squared plus 0 squared. Oh, that's easy, guys. What's 4 squared plus 0 squared? 4 square rooted. Times 4. Now, if you guys want to, I don't know, save yourself a little bit of work plugging into your calculator, I guess you could be super snazzy and say 3 over root 13. But what are we doing anyway? Yeah, we're still plugging and chugging. Somebody find me that angle in degrees, please, and that's not a unit circle. No. Remember, chapter 6 is definitely a calculator chapter. Make sure you have a calculator with batteries that work, that you understand how to use for the test on Thursday. Cool? Coolio. Cool dealio. Error. What?
33.690.
Dun, 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 dun. Nice.
What do you want to do?
Are we okay? Practice the dot product, practice the magnitude, plug into the formula. Sweet. Is that cool? Another application.
What is that word?
Orthogonal.
Oh, that's quite a
sounds fun.
word.
Now, I introduced you guys to the idea, was it last week or the week before? What does normal mean in math? Perpendicular? Ah, what else means perpendicular? Orthogonal. Did you guys say it yet?
Oh,
Orthogonality, that's a snazzy word. Two vectors are orthogonal if and only if their dot product equals 0. There's a reason as to why. We're going to kind of get to peek at it, but not stress too much about it. But double check your notation again, guys. We got vectors all over this page. Make sure you classify them. Vector, 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 vector. And maybe not that many, but you do have quite a few. So if a question asks, determine whether they are orthogonal. I guess we could graph them very precisely on graph paper and get out a protractor and see if there is truly 90 degrees in between, but maybe just do a dot product instead and see if the dot product is 0. Yes, or they both have to be equal to opposite. You know what I mean? What's weird about the example below though? Can you guys see it? There's no J on vector U. Instinct. How do we rewrite that then? Yeah, does that make sense? So we can see this as 1I plus 0J. If we want to do the dot product because they said, hey, is it orthogonal? We're like, all right, cool. Is the dot product 0? Well, wouldn't we have 1 times negative 2 first? Plus 0 times 2 second? What's the dot product? Oh. Well, what does that mean? Exactly. If the dot product is not 0, then we can say they are not orthogonal, which means they hit at some sort of angle other than 90, right? 90, you got messed up something. Not orthogonal. What if the dot product had been 0? Orthogonal. As easy as that. You guys got it? Yeah. Okay. Oh, cool. Now, this, ready? What's the green? Big old parentheses to say we're going to talk about it, but I'm not going to require it for the test. Sound good? I would like it in your notes because if you take this to college and you take a physics class, it might be nice to have. Okay, that was a fun idea. Long story short. These applications are for when, for instance, you have a box on the ground and you have a rope around the box or somehow connected to the box. And you're trying to drag it along the ground by, I don't know, say pulling it over your shoulder. Pulling what over the shoulder? The box? No, the rope. If you're trying to pull something with some sort of rope. So, for instance, if you had some sort of, let's see, how can I show this? If you had a box here, and you're trying to move it this way, and you're up here with a rope slung over your shoulder, pulling this away. So you're pulling at this angle, and yet what you're trying to result in is this movement. This is called projection. Projection is you have some sort of movement going on up here, or some sort of force, but that's not where the box is going. Your goal isn't to literally pull the box up that way along vector u. Your goal is to let the box be moving along vector v. My v dot turn out so pretty. What's the answer? You guys kind of get what I'm saying? This is you. You're pulling this away, but where's the box actually headed? That way, along the ground. Okay? That's what the idea of projection. Projection is you have some sort of force U being exerted in U's direction. We say it's being projected onto the other vector where the movement is actually headed. Now, just because they say the word projection doesn't mean there's a snazzy word problem going on. It could just be something like example 66 down below. So let's go ahead and try to do example 66 and see if we can figure out exactly what's going on with how to plug into this formula. The question is basically if, oh, I didn't label them, I'm sorry guys. If we have a vector u, we have some sort of force being exerted this way, what does it end up resulting in this way as it's projected down onto it? I'm going to undo those nasty circles. That's u, let's call this little dude v. Oops. We have terminal points from which we can figure out components, right guys? So since we're trying to do u onto v, we have to be very specific with our formula or else we're going to get in some trouble. Projection of u onto v is, okay, how do we do dot product? U dot v, which is going to be 12 plus negative 12. Is that good? 12 plus negative 12, 6 times 2 and 3, nope, 4 times negative 3. All over. How do we find the magnitude of v? Yeah, Pythagorean. Take these components and what do I do to each of them? Square them. And then what do I multiply this by? You see it? V. Who's vector v? This guy. You guys see how I plugged into the formula? Let me zoom in. I have my dot product on top all over the magnitude of v, which is just Pythagorean being squared, times the vector v. Now what do you end up getting? 12 plus negative 12. Wait, what's that? 0. All over 13 times 2 comma negative 3. But hold on, kiddos. 0 over anybody is still 0, right? What's 0 times anybody? 0. What's the projection? Does this force have any effect on this movement? No. Oh, I wonder why not. Hey, exactly. If we see this dot product being 0, these are orthogonal. If they're orthogonal, they're happening at 90 degrees to each other. If they're happening at 90 degrees. If you're pulling up on this box and he's not actually moving, is he going over at all? No. He's stuck. He's just chilling. So just because there are two different vectors doesn't always mean that there's an actual projection occurring. If they're orthogonal, the projection will always be 0. But kiddos, does the plugging in make sense? Okay. Remember, we're just playing around with the math. The math is a formula that will be applied much more in physics. So this is pretty much our last one. We're not going to start 6.5. That's okay. We'll do all of 6.5. I'll trim the fat off of it. We'll do the short and sweet version. There are technically two different formulas for work. There are technically two different formulas for work. But the nice thing is, kiddos, why don't we just go ahead and circle one of them? Sound good?
Oh, that sounds wonderful. Oh, yes. Awesome.
Work equals force times distance. Wait, that's a thing. Hopefully you learned in physical science way back when. Work equals force times distance. Force times the actual distance of movement. Meaning, if you're pulling and pulling and pulling and the thing isn't actually moving, technically no work is being done. You're like, but I'm sweating. Doesn't matter. That stinks. I know. Sad times, huh? Yeah. Technically, work is defined to be force times the actual distance being moved. So as you guys are hopefully not stressing about the picture, instead just getting the formula. Let's just see if we can do a little bit of work down here to find the work being done. Work is equal to the force vector times, or I should say dot product with the movement. The force in this one, they said was V, so I'm going to make it negative 2, 3. Wait a minute, kiddos. Did you figure out how to take an initial and terminal and figure out the components? What do you do? How can you tell know how it went from P to Q, what would the components be? You say, what happened in between? -3 minus 1 and 5 minus 2. So we can say terminal minus initial is what's really going on. We end up with -4, 3. Dot product with -2, 3. The dot product simplifies so we don't have to use this nasty formula up above. And we can just do a simple dot product with the force and with the distance, and we end up with horizontal times horizontal, 8, plus vertical times vertical, 9. What's the work being done? 17. 17 what? I don't know. Sorry, they didn't give us units, or I didn't give you units. But we can say that is the work being done in moving the particle from P to Q with the force of P. Not too shabby, huh?
Yeah.
Look at those. Homework. It's not that. Your homework's easier than that.
Okay.
That's from a couple years back, so I don't even know.
Okay.
All right, cool kids. You know what to do. Homework is done. Read the short, sweet version of 6.4 with the short, sweet version of 6.5. Okay, calculators.